The Australian Water School extends a warm welcome to everyone joining us today for this critical webinar on integrated catchment and receiving water modelling. The team here are delighted that you've been able to join us, and well over 1,000 people registered for this webinar. You can see there on the screen now, right across the globe. Michael and Phil are going to be the presenters, and Emma and Chris are on the panel. Emma will chair the Q&A. So come on screen, everyone. Michael, Phil, what drives you? What keeps you awake at night? No, maybe that's not it. Maybe, as Joel said earlier, what gets you up in the morning?
Thanks, Trevor. What gets me up in the morning, I just love being able to be in an industry where we can make a positive contribution to our environment.
Yeah, great comment.
It's all about for me.
Yeah, great comment. And do we have Phil? Yeah, we do. Sorry, that. Yes, I see that.
Yeah, what gets me up in the morning is usually kids.
Yeah, well said. I know the feeling.
But in terms of work, I mean, helping to solve problems, and as Michael said, making a positive contribution.
Fantastic, Chris, Emma. Thanks for joining us so much. Appreciate that. Chris is going to be on the lines along with Emma on the Q&A line. So get your questions in, get them early, get them often. All right. Well, let's kick this off then. We'll start off with Michael.
Thank you, Trevor, and thank you, Joel, and for hosting us. Today, it's lovely to be here talking with Phil about integrated catchment and receiving water modelling. So today, we'll cover why undertake environmental modelling very quickly. Then we'll talk about a particular type of environmental modelling, which is integrated catchment and receiving water modelling, which will be the focus of today's webinar. And we'll talk about just a little bit about some limitations of some historical methods of executing this modelling, and what really matters about some of those limitations, and therefore what motivated the solution that we'd like to chat about a little bit today, which is TUFLOW Catch. And we'll talk a bit about how we've applied TUFLOW Catch to Oxley Creek in southeast Queensland. So really, to talk about the why, why do we do environmental modelling? Well, really, environmental modelling is about providing evidence-based support for decision-making. Environmental models don't make decisions for us, but they certainly contribute to the decision-making process and are a very important part of it that we rely on. The sorts of questions we might ask of environmental models. Is a farmland area revegetated? If a farmland area is revegetated, or there's a new urban development to be put in somewhere in a catchment, what impacts does that have on the downstream water quality of a creek or a river those areas might drain to? So it's really about looking at the connectivity between what happens in a catchment and what happens in a receiving water. And it sort of motivates the question, well, why are we interested in the quality of receiving waters? Often, not always, but often there are legislative imperatives in the receiving waters, and they're things like local or state or sometimes federal governments might mandate that water quality needs to be of a particular standard in a particular waterway. It might be measured as an annual median. So those targets need to be met. So we need to work out how to meet those targets, and often modelling and modelling studies will play a role in how we go about doing so. And indeed, I think more broadly that if we are environmental professionals, whether we're modelers or not, then I think it really is part of our responsibility to assist in the custodianship of these rights. Really make sure that we're doing the best we can to preserve their quality for future generations. So let's talk a little bit about now, rather than why we do this, but what we're actually going to talk about today, and that is integrated catchment and receiving water modelling. What is it? Well, this type of modelling simulates surface and subsurface water and pollutant flow in a catchment, really from the top of the catchment all the way down to the receiving waters and then exiting of the catchment through those receiving waters. So we simulate water flow, and we simulate the pollutants or constituents that they're sometimes called that go with that water flow. And some of those pollutants include sediments or nutrients or pathogens or sometimes pesticides. But really it's up to the study and the sorts of questions that are being asked as to what those pollutants are But we'll always simulate surface and subsurface water flow with whatever pollutants we're interested in. And we'll certainly simulate those processes in the catchment and the receiving water. And that's what we'll talk a little bit about now. So in the catchment, which is the upstream side of the modelling, the integrated modelling workflow, we will always simulate rainfall runoff. And that is trying to predict hydrologic responses of a catchment in the surface and the subsurface to rainfall. There are many, many ways of undertaking that modelling and many different models and algorithms that are used. But in some form, fundamentally, we're trying to predict water flow as a result of rainfall, both in the surface and subsurface in our catchments upstream of our receiving waters. And as I said, we will also try to predict pollutant export and transport that is associated with that hydrology. Now, in the space of integrated catchment and receiving water modelling, the predictions that are made from these catchment models, both in terms of hydrology and pollutant export, are used as inflows or boundary conditions to downstream receiving water models. So what we're really going to talk about today is the importance of accurately reflecting on-ground conditions when we're going to take our hydrology modelling, so that those boundary conditions or those upstream conditions that we apply to our receiving water model are as reflective of reality as possible. So this is what we'll be talking about mainly today. Once we have undertaken our hydrology modelling or upstream modelling, then we also need to simulate our receiving waters. And we talked about some of those receiving waters being creeks or lakes or coastal oceans areas. And these models, they take those predictions from the upstream hydrology models and use them in their calculations of water quantity, flow and quality in these receiving waters. In the receiving waters, we will always simulate hydrodynamics. That means water flow, velocities, water levels, water depths, and often salt and heat. We'll also simulate often sediment transport and any number and range of water quality constituents. And again, those water quality constituents will need to match in some way the water quality pollutants that have been simulated in our catchment model. And again, they might include nitrogen, phosphorus, pathogens, sediments, or some boutique pollutants such as pesticides. But again, it comes back to the questions that we're asking of our models and therefore what we need to simulate. So in order to undertake integrated catchment and receiving water modeling, we need to link catchment models and receiving models together. And that is something that in concept at least has been happening for a very long time. I certainly remember in the late 1990s, early 2000s, first came across this sort of modelling and the need to link catchment models with receiving models. And the reason we need to do so is because we are typically asking questions about if we do this in the catchment, what happens in the receiving water. So we need to have both those models working together through some form of linkage. The linkage has been happening for a long time, but not always and not everywhere, but certainly for the majority of studies that I've been involved in my career so far, there is often a disconnect or a misalignment between catchment modelling conceptual approaches and outputs and the needs and requirements of downstream receiving water models. Even though we try to link them, they may not be as well aligned as we'd like. And this is not all the time for all cases, but certainly the majority of cases I've come across. Some examples of misalignment is, for example, a temporal resolution of catchment models. Might be daily, it's not always, but it's often daily in my experience. And yet the receiving water models we typically run might be running on seconds time steps or even less than seconds. The spatial resolution of catchment models might be square kilometres, not always, but often square kilometres. And yet our receiving models will have resolution in our creeks and estuaries and coastal oceans down to perhaps square metres or cubic metres if we're running in 3D. So there are often disconnects in the way that models are being constructed and built as software, because they might not have been known about each other when they were being built And so we sort of inherit catchment models and receiving models after they've been built and constructed with these sorts of assumptions in them. And we try to link them together through some transition process. And that transition process is not always smooth, and it's not always easy, and it can lead to conceptual and interpretive difficulties when we come to actually using these models to inform decisions. So what I found over the years is that the better we can match the conceptual design of our upstream catchment model and downstream receiving water models in this integrated approach, the better we can transition information between them, the better we can support informed decision making. And so what we've found really is that the rigor of catchment model predictions in terms of hydrology and pollutant export really can directly influence the predictive power and therefore usefulness and utility of receiving water models, because catchment models deliver information downstream to receiving water models. So depending on the questions being asked, we could say, well, does this misalignment really matter? Does it matter that we might run our catchment model on a daily time step and our receiving model on a seconds time step? Well, it depends on the sorts of questions that are being asked, but today we'll talk about one case study where it does matter. Here's an example, just to get us started. Here's an example of some predictions from a catchment that we'll talk about again shortly, but this is just an introduction to some of the information we'll present in more detail later. Here is information from a receiving water model of Oxley Creek, which is in southeast Queensland. There's two panels and they both span 1 year in time. And the predictions in the bottom panel here are salinity at a particular point in Oxley Creek. So it's just a time series of predictions of salinity. From January 2019, this happens to be until the end of the year. And in the top panel, we just have over the same time period, we have two different ways of estimating, two different estimates of the hydrology entering Oxley Creek over that time from two different catchment models. One is TUFLOW HPC and one is a lumped daily model. The blue line in both cases is, in the top panel is TUFLOW HPC predictions, and the orange line is the daily model hydrology predictions. And you can see they're different. So what this graph is, what this figure is showing is that when we have our receiving model taking the different hydrology predictions from different models, we see we get a very different response in salinity predictions downstream. In fact, we find that the blue hydrology, which is from TUFLOW in the top panel, gives us the blue predictions in the bottom panel for salinity, and the orange predictions for hydrology in the top panel give us something similar. Give a similarly coloured line in the bottom panel, which is the recovery of salt as a result of forcing the model only with the upstream hydrology from the orange line. So really what we can see is that by changing nothing else other than upstream hydrology, we can get very different predictions downstream, which just goes to underscore that getting our hydrology upstream to be reflective of reality, reflective of what's happening on the ground, is really, really important because it can directly impact the predictive power of our receiving models. So does this misalignment, this potential misalignment between catchment models and receiving models matter? Well, it can. It can, and we're going to talk about a case study where it does today. And we always come back to the sorts of questions that are being asked, and sometimes it may not matter, but certainly in the majority of cases I've come across it does matter, and it matters a lot. And that's what's really motivated us to start talking about TUFLOW Catch. And TUFLOW Catch is a product that we're developing now with some colleagues and with co-funding support that tries to overcome some of these misalignments that we have experienced as modelers over the last 20 to 25 years. And by doing so, we are building a product that we really hope will improve predictive capabilities both in the catchment hydrology side and the receiving water side, such that the linkage between the two is much more seamless and scientifically robust. And have these models know about each other and be designed and tailored to work together well, rather than taking separate models together and trying to bolt them together later on to answer potentially complicated environmental questions. So what we've done is we've taken two existing TUFLOW HPC, and we've used that and upgraded that to prepare our catchment hydrology predictions. And we've linked that with TUFLOW FV, which looks after the receiving water modelling. Between those two products, with considerable enhancements, which Phil will talk about in a minute, we have developed this product, which we hope really goes some way to addressing the potential misalignment as we just talked about. We undertook this work with our very good colleagues at Alluvium Consulting at Griffith University, and we did undertake this work in grateful receipt of funding from the Queensland Water Modelling Network, which is a Queensland government organisation here in Australia, and Healthy Land and Water, and we're very grateful for the co-contribution that those organisations made to this work. So Phil, over to you.
Excellent, thanks for that, Michael. Yeah, so I guess that does draw the question, what is TUFLOW? And you were speaking about TUFLOW HPC and TUFLOW FE. Well, TUFLOW is primarily two products, namely our fixed grid and flexible mesh numeric schemes. Inside that fixed grid solvers, we actually have two solvers, TUFLOW Classic and TUFLOW HPC. Both of these are 2D with 1D functionality, which allows modelling of subsurface pipes and even open channels and things like that. TUFLOW Classic is a finite difference scheme, which has been around since the late 1980s. Obviously had a huge amount of development since then, but due to the numeric scheme, it's really well suited to single core kind of processing, which with the hardware available at the time was very efficient. But as things have moved on, CPU and in particular GPU have really moved towards parallel hardware. So multiple computational cores on a CPU or a GPU. So TUFLOW HPC is a finite volume solver, which started development in 2017 or so, and it's really been designed ground up to allow distribution of calculations, primarily across GPU cores or multiple GPUs, but also across multiple CPU as well, CPU cores. So notably for this catchment modelling, we're using TUFLOW HPC for a number of reasons, primarily speed, which is, I've just talked about, stability, and also to utilise the subgrid sampling functionality we have available in TUFLOW HPC, which allows us to use elevations at a much higher resolution than the 2D cell size. And finally, TUFLOW HPC also has some groundwater functionality to model vertical and horizontal movement of the subsurface flows. So I guess that's the fixed grid component. TUFLOW FV on the right-hand pane in the image there is our flexible mesh solver. And so TUFLOW FV can simulate advanced 2D and 3D hydrodynamics, river, estuary and coastal environments. It can be coupled with sophisticated sediment transport, water quality and particle tracking functionality. It also allows running on GPU and integrates with atmospheric and ocean boundaries from global meteorological and ocean circulation models. Typically used for 3D flow problems, large scale and longer term simulations, where environmental sediment processes are important to represent. So that's, I guess, TUFLOW products in a minute or more. A lot of the functionality that is required for this catchment modelling, such as the ability to do direct rainfall, like rain across the model, and the groundwater flows, they're already part of our TUFLOW HPC offering. Specifically for this TUFLOW Catch, we needed to make some changes in HPC to allow additional functionality. One of the main components was pollutant export. So allowing the water to generate those pollutants. So that's done via an accumulation. So over time, the pollutant is accumulating on those dry cells. And once that becomes wet, they are released into the water. So an accumulation rate, nominally in kilograms per hectare per year, is set for each land use type. And those land use values are applied on a cell-by-cell basis in the HPC model. So when that pollutant release is occurring, we actually have some options for setting a minimum cell depth and a rainfall rate before we're allowing that dry mass of the dry store to be released into the water. And there's also a release rate which controls how quickly the pollutant can move from the dry mass store into the water column. And that exported pollutant can then be transported into either the surface water and also the subsurface, the groundwater flows. It is actually possible to prevent pollutants from making it into groundwater. So things like particulates, we might actually limit those so that they only stay in the surface water. And there are a range of parameters required by the receiving water quality TUFLOW FE model, which potentially can't be modelled via an accumulation release approach. For example, temperature or salinity. However, we can model these either as a time series or a constant boundary instead. So in addition to the pollutant export described in the last slide, we've also made some enhancements, particularly for the linkage between the catchment and the receiving model. And this is really important, as a manual or a semi-automated linkage can be fraught with error. Double counting flows or missing flow locations can mean that the receiving water model is getting too much or too little flow, not due to an error in the catchment model, but in terms of how those two are being stitched together. So the TUFLOW HPC is able to interrogate the TUFLOW FE mesh and the boundary locations in order to determine the spatial connectivity between them. And this includes both node string boundaries in TUFLOW FE, which are typically applied across a waterway or a tributary and have an allowance for momentum, and any other locations we're applying those as a lateral inflow. And we're writing the boundary data out from TUFLOW HPC for all the required constituents at all the required boundary locations, as well as additional information like mass balance and things like that. So in terms of a pilot model, as Michael mentioned earlier, Oxley Creek in southeast Queensland has been used. It's a catchment area of about 260 square kilometres, and it drains to the Brisbane River. So the maximum elevations in the upper catchment are around 300 metres above sea level, and the lower sections of Oxley Creek are tidally influenced. So that gives us an idea of the range. It contains a mixture of land uses, primarily forested in the upper catchment and urban in the lower catchment. And this mixed land use and the data availability was some of the reasons that we actually chose Oxley Creek as a pilot for this modelling. In terms of the TUFLOW HPC configuration, it uses a direct rainfall approach. There's a number of rain gauges in or near the catchment, and these are interpolated within TUFLOW into a spatial and time-varying set of gridded rainfalls, essentially. It also has evaporation over time being applied. And those that have been to some of our previous AWS TUFLOW webinars, particularly on direct rainfall, are probably aware of some of the benefits of subgrid sampling, particularly in terms of direct rainfall. So in this case, we've got a subgrid sampling distance of about 1 metre. So one of the first things we did early on was to do a cell size sensitivity. So we ran the model with a range of different cell sizes, keeping the subgrid sampling distance at 1 metre to compare the flows into the FE model at a range of cell sizes. And following that, we adopted a 60 metre cell size as giving consistent flows compared to the higher resolution model, whilst giving us some shorter run times. So run times for this modelling was about 3 hours for a year of simulation on a NVIDIA RTX 4090, and so on a GPU. The HPC model uses soil infiltration and groundwater, and whilst this can be varied on a cell-by-cell basis, this pilot modelling was using a consistent vertical soil profile across the catchment, and that was using properties that came from the Australian Soil Atlas by CSIRO. And the groundwater approach that's used in TUFLOW actually allows groundwater to recharge back to the surface water at any cell based on the surface and the groundwater levels and gradients. And we did do a calibration, which I will talk a little bit about, but yeah, standard parameter ranges, for Manning Zs and things like that. So as part of that calibration, we've got a couple of plots here. We've got a year-long time series at the Beatty Road gauge, which is highlighted there in the image on the right, which is the most downstream gauge in the catchment before it goes into the receiving water model. So we ran 3 annual periods, so obviously presenting just a single location for a single result. If we look at the periods in that where we've got higher rainfall and flow, now, for example, in May there's a couple of rainfall events that are close together, and we see a spike in flow. And after that rainfall, we can see that for weeks or even months after this rainfall, there's a low flow still coming in through that gauge. And looking at the model results, we can see it's capturing that quite well. And the groundwater and the recharge from the groundwater is quite important in that regard. So even with a direct rainfall model, without groundwater, it's hard to get that those receding limbs modeled really nicely. Then the exceedance plot on the right or in the middle there shows that there are flows in the creek for a significant amount of the time. Over 70% of the time there are actually some flows in the creek. And the pink and the black line there are the observed in the model. So this is showing us that HPC is able to predict not just the peak flows, but also the flows during those drier periods as well. Okay. And so, as I mentioned earlier, the linking of that, the catchment and receding models, it's determined by the flexible mesh and also the HPC resolution. So if we wanted to change the resolution of that, it should be a simple matter in TUFLOW, just changing the cell size is a single number in a control file, and that will change the configuration of the HPC model. Because of the automation of the linking, that will update all of the linkage locations and things like that, to avoid that potential issue of undercounting or double counting flows. So in this case, the image on the right there shows those locations, and we've got a different temporal output frequency for the main river channels, the node string flows into TUFLOW FE, and also the laterals as well. So I guess that's a summary of the catchment model for the Oxley Creek in terms of the catchment. And I'll hand back across to you, Michael.
Thanks, Phil. And I think it's really, really wonderful as a receiving modeler to see that automatic connection of catchment inflows. We can see the 920 odd points that are done automatically. It's just wonderful because it gives us that really nice, smooth connection between the two models. So that model that is the receiving model is TUFLOW FE, and unlike HPC, we didn't undertake too many enhancements of TUFLOW FE for this particular pilot study. It was always going to be the case, and didn't really need too much more additional work. But a bit of an overview of the model itself, Oxley Creek. It's 3D hydrodynamics with about 12 vertical layers and a few thousand lateral cells. And we did include the advection dispersion, sediment transport, and water quality modules as part of the simulation. Very standard parameters in the TUFLOW FE model. It's about 10 hours, 9 to 10 hours for a year's worth of simulation. So it's something we just leave overnight. We simulated salinity and temperature with one sediment fraction, as well as oxygen, silicate, inorganic nutrients, organic nutrients to one generic phytoplankton group. And we had atmospheric forcing applied to the TUFLOW FE model from CFSR, and we prepared those boundaries using one of TUFLOW FE's free Python tools called GetAtmos, which is available to everybody to do something similar. We ran it for 2019. This is just a schematic of the water quality processes simulated. I spent a lot of time on it, but at the core of the simulation is dissolved oxygen. And of course, that interrelates then with inorganic nutrients. Organic nutrients, just labile, and a phytoplankton species, with all these different constituents interacting either with the atmosphere or the bed as required. We have silicate off to the right because our phytoplankton species uptook silicate as part of its chemistry that we'd set. So in this pilot model, TUFLOW FE, we ran it over 2019, as I said, and of course we went through a calibration process, of which I'll not explain all the details now, but I will show some calibration plots with regards to salinity predictions in Oxley Creek, and that's because salinity often reflects hydrologic inputs to the receiving model, which we've talked about before today, and their importance. And I'll talk a bit about sediment as well, that calibration. The reason being is because that calibration performance reflects the pollutant export properties or characteristics that are applied to the FE model, again from the upstream catchment model. All the measurements I'll show you, all the predictions I'll show you will be compared with measurements, in-stream measurements, and those measurements are from surface waters, and they're a snapshot in time. They're not a daily average or anything, they're a snapshot in time, an instantaneous measurement, but we'll compare our model results with those. And of course, when we take those sorts of snapshot water quality measurements, they cannot capture intra-day variability due to tidal fluctuations, for example. So we won't see that in the measurements, but we will see it in the model predictions. The locations that we'll look at in terms of this calibration performance for salinity and sediment, I've labelled A, B, C, D, and E. All we need to do is remember that A is at the mouth of Oxley Creek down here, and E is near the headwaters of Oxley Creek, certainly the tidal section, and B, C, and D are intermediate stations in that water. So here we have time series of salinity. On all these subplots, we go from January 2019 to December 2019. And as I said, we're looking at 5 stations, 5 locations labelled A, B, C, D, E, from mouth to headwaters or downstream to upstream. In all figures, the TUFLOW FE predictions of salinity are the blue lines, and the in-stream measurements are the yellow dots with the red border on them. And the very bottom figure here, I will have salinity plotted as the blue line, but I've also overlain the hydrology entering the model at the time, and this has come from TUFLOW HPC. So here's a time series of hydrology over 2019, which is just inflow at the upstream end, which has been automatically generated by TUFLOW HPC, as we've seen. So the first thing to notice in this figure, of course, is that we do have intraday tidal variability in our predictions of salinity, as we expect in a tidal system such as Oxley Creek, which is why we have this blue line going up and down sections, but it's not reflected in the measurements. That's why, because in the measurements it's a snapshot in time, but the model has the whole day simulations. That's why I get this blue line going up and down, but these measurements don't do that. The most obvious feature, I think, initially is that we have suppression of salinity concentrations in Oxley Creek over this period here. Why? Because we have freshwater inflows coming from upstream, as predicted by TUFLOW HPC, entering Oxley Creek. And when those freshwater flows come in from upstream, they push salt downstream out of Oxley Creek and into the Brisbane River. And that's why we see in these sites that are from the upstream to the mid-estuary, we really don't have much salt in there at all, as predicted by the model. And that's also borne out by the measurements, which again are the yellow dots. So this salinity suppression thing is something that's important. We need to make sure we're getting that right. And that is strongly driven by the inflows coming from TUFLOW HPC. The other and parallel or complementary, I suppose, process is salinity recovery in Oxley Creek. And what that means is that when these inflows from TUFLOW HPC eventually recede to a point, they then allow salt from downstream at the mouth of Oxley Creek to migrate upstream eventually over many, many tidal cycles and recover, as we say, up the creek from site B to C to D to E. And of course, this recovery is well predicted by TUFLOW FE. The yellow points to the measurements, and you can see TUFLOW FE in terms of its general rate does a really good job noting intra-day variability, does a really good job of reproducing these measurements, these salinity measurements. When it rains again, we get a little bit of an inflow from HPC here, and of course salinity then drops in the estuary as expected. Why? Because the fresh water coming in from upstream has flushed that salt. So this salinity recovery is a really important thing to get right in a receiving model when we're looking at integrated catchment and receiving water modelling, because it talks to the balance between inflows and in-stream hydrodynamics. We need to get that right if we're going to move to water quality. So that was a good outcome for us. Looking now at sediment, it's the same 5 panels from top to bottom, sites A to E, but we're not plotting salinity this time. We're plotting sediment concentrations, where again the blue lines are model predictions and the yellow and red dots are measurements. And we're plotting sediment again over 2019. The first thing to notice again, of course, is we have our intraday sediment concentrations, and that's because we have our boundary conditions coming in and out of the model on a tidal basis, and we don't pick that up in the monitoring data because it's a snapshot. But the model is in the right ballpark according to the monitoring data, despite that intraday variability. The next thing to notice is that in contrast to the salinity plots, we actually have sediment concentration spiking during this time where we know we have inflows coming into the catchment. Why is sediment spiking in the receiving water? Well, it's because water is coming in from TUFLOW HPC's predictions and bringing sediment with it. And that's why we see when it rains, which is the black line here, we get spikes of salinity following through the estuary. And there's a nice correlation, obviously, between inflow and concentration spikes of sediment. Again, conversely, when the inflows from upstream recede, we don't have really much inflow at all down there for quite some time. Before, when we saw salinity recover, increase, we're actually seeing sediment level out here at equilibrium concentrations. So we're sort of flatlining with sediment here in stream. We do have this variability in period, and that's about 2 weeks. We have resuspension of sediment going on in our creek, which is strongly related to the neap and spring tidal cycles, which is why we get this sort of fluctuation on a 2-weekly basis of sediment concentrations, which is really nicely picked up by the model and reflected in emissions. So given that, we're really quite happy with our hydrodynamic and sediment calibration model. I haven't shown you all the calibration for time reasons, but I hope that gives you a flavour of how well the model is performing in the receiving environment. What we're going to do now is show you an idea. I'll give you an idea of how this linkage that Phil was talking about between TUFLOW HPC and TUFLOW FE is actually being applied and what we can do with that. And Phil did say it, but I'm going to say it again. It's all automated. And for a receiving water quality modeler, that's just fantastic because there's so much time and effort that's required to do that manual linking when models haven't been built with each other in mind. To have that done automatically is just a fantastic gift. And so what we can show now is some of the powerful scenarios and model runs that we can undertake with that automatic linking in place very, very easily now without having to redo all that manual linking. And as Phil said, with the potential to under or double count. So we're going to play an animation in a minute, but to explain the panels, the top left-hand side here, we have a plan view of Oxley Creek catchment. Here's the top of the catchment, here's the bottom of the catchment. And what you'll see is rainfall falling over this as the animation starts. It'll be green colour. And when it goes dark green, you'll know it's raining. TUFLOW HPC takes that rainfall and converts it into surface runoff and subsurface runoff. But what we'll see on this figure then is the resulting surface runoff that appears as predicted by TUFLOW HPC in the Oxley catchment. So it's a transfer of rainfall to surface runoff. And then what we'll see is how that surface runoff and HPC automatically interacts with TUFLOW FE's salinity predictions downstream. This bottom pane is a curtain or a vertical profile of salinity concentrations from upstream here to downstream here in Oxley Creek. The colours correspond to the colour bar on the right-hand side, and they are salinity. So blue is 0 salinity and red is 25 grams per litre salinity. And you'll see this go backwards and forwards with the tide when the simulation animation starts. And that's just tidal pumping of salt as we expect. So the blue star here on this end of the curtain cross section is upstream end here, and the red star is the mouth here. So what we should look out for is rainfall moving from here to become surface runoff to then inserting itself into the Oxley Creek TUFLOW FE model, a whole range of locations along this curtain profile. So there's the tidal pumping of salt in Oxley Creek, and then it rains, water gets converted to surface runoff and then immediately runs into Oxley Creek, flushes out all that salt, which runs downstream. And then that flushing mainly came from localised urban areas here. And now all the water that's come from the surface, upstream parts of the catchment, is arriving now in Oxley Creek and pushing up the water level here. Obviously the water's all fresh because it's come from the catchment, so it's blue. But really this is just an automatic linkage between rainfall, runoff, and then what happens in the downstream receiving environment. With a little bit of salt trying to creep back there from the boundary as the simulation finishes. So that's salinity and water flow. What we'll do now is we'll have a look at exactly the same time period, except we won't look at water flow and salinity. We're going to look at sediment concentrations. So on the left-hand side, this top panel, we don't have rainfall anymore. What we have is the dry store of sediment in the TUFLOW HPC model that has been computed as a result of user-specified accumulation rates that Phil talked about earlier. The red stores are high stores and the red areas are high stores and the blue areas are low stores. The red areas more or less correspond to urban and industrialized areas, and the blue areas correspond to forested areas. So that's why they're different to start with. There's a lot more sediment that's accumulated in the urban compared to forest areas. What we'll then see is these dry stores get converted into wet concentrations in the water that is flowing across the surface in TUFLOW HPC. So you'll start to see some red spikes pop up in colour contours, which represents high concentrations of sediment, surface water, and they'll run down into the Oxley Creek model, for which we can then see not a curtain of salinity, but now a curtain of sediment from upstream again to downstream. And instead of plotting salinity in the vertical, we're plotting sediment from 0 to 40 milligrams per litre. So red is 40. So what we'll see, we'll play this one and we'll again see a transfer from here to here to here. So there's the same tidal pumping in the bottom screen of sediment. The surface stores disappear on the left. They become surface runoff and run immediately into the Oxley Creek receiving environment as pulses of sediment. And what I really like is that the red pulses of high concentrations come immediately into the creek from urbanised areas. But now as the water level rises in Oxley Creek, we're getting much lower concentrations of sediment entering the system. Why is that? Because the majority of the land uses upstream of the TUFLOW FE model are forested, so have low concentrations and low sediment stores, low dry stores of sediment. So this is just an example of how we can link these two things together. I'll play that again so we can just see a lot happens. Going from dry store to concentration to insertions of red high concentrations into Oxley Creek as the water level rises. At those, 900 or so connection points between the two. And then the lower concentration water comes in the top end again, the bluer colours as the water that's come from the forested areas arrives at Oxley Creek with the delay we'd expect with a catchment this size. Now what we'll do is we'll play exactly the same information, except we're going to zoom right in now on Oxley Creek around the TUFLOW FE model. So it's exactly the same time period and rainfall event as I just showed you for sediment, but we've zoomed in and we've put some arrows here on the curtain, red, yellow through to the darker colours. And these point to locations in the curtain that are parallel locations in plan view here. So when you see a disconnect in colour contours, say at the yellow arrow here, you'll be able to see that that's because there's an inflow coming in at the yellow arrow plant sediment. So what we'll do is we'll play the animation and you'll see the colour contours of sediment appearing at the surface here, and the colour contouring is the same from 0 to 40 in both these images. We'll play it now. There's a tidal pumping of sediment in the bottom, but then it rains. And you can see the surface sediment concentrations rolling into Oxley Creek and delivering that high concentration of sediment to the creek itself. And again, the cleaner, slightly cleaner water from upstream then begins to arrive into the system as bluer colours. So this is really just a qualitative example of how we can exploit the power of this modelling system now that we have TUFLOW HPC's ability to simulate the accumulation of dry stores and the transfer of those dry stores into wet concentrations that then transfer in Oxley Creek to the three-dimensional TUFLOW. It's done seamlessly in the background. Okay, so why does this matter? Well, it does matter because we talked about like salinity recovery a little bit earlier. So what we've done is we have taken exactly the same TUFLOW FV model, except we have replaced the catchment inflows provided to that TUFLOW FV model with catchment inflows from an existing daily lumped hydrology model. That lumped hydrology model is currently in use. To be very clear, Trevor, that current hydrology model has not been built with the intention of solely forcing Oxley Creek. It's been built with the intention of providing flows to the broader region. But because it was in existence, we used it just as an example of sorts of change we might expect to see by changing nothing other in a TUFLOW FV model other than the hydrology that forces it in the catchment. So it's in use, but was designed for other environmental questions, taking us right back to the beginning of the webinar. So we'll look at very quickly, we'll look at salinity and sediment predictions at site C in the middle. Again, the blue stars are the headwater and the red star is at the mouth. Salt, nitrogen, phosphorus coming from the mouth, and freshwater the headwaters. So here's an extension of the first figure I showed you way back at the beginning of the presentation, with flows in the top panel and salinity in the second panel. But we've added now nitrogen, phosphorus, and chlorophyll as three other things that we predicted in our TUFLOW FV model. The blue lines in all cases are those predictions associated with TUFLOW HPC predictions of hydrology, which is these blue lines here. So this blue line and this blue line and this blue line are resulting from the hydrology predictions of TUFLOW HPC. And the orange lines for salinity, nitrogen, phosphorus, and chlorophyll in the TUFLOW FV model are resulting from forcing the model with the lumped daily hydrology model, which is the orange flows in the top panel. So the first thing we'll look at is this wet period, where clearly, as Phil mentioned, TUFLOW HPC has predicted this falling in over several months in some cases of water continually coming into Oxley Creek. The implication for that is that the TUFLOW FV predictions of salt, as we talked about, are such that salt concentrations with the blue line are suppressed, which means that there's fresh water coming in the top and salt is not able to ingress back up the estuary because of that. The contrary, or something contrasting, applies when we force the TUFLOW FV model again, not the HPC predictions, but the lumped daily model predictions. We get much more salt coming to the estuary. Why? Because salt can come further upstream because there's not the falling in happening in freshwater hydrology coming in upstream. Similarly, we see differences in concentrations of phosphorus and chlorophyll this time between the orange and blue lines in the TUFLOW FV model. And we generally see more nitrogen and more phosphorus and more chlorophyll coming into the system, the orange line and the blue line. This is because nitrogen and phosphorus are also being transported up Oxley Creek with salt as a result of the lower freshwater inflows that are being the hydrology in the top figure. So it's entirely consistent with what's happening in salt, but slightly modified, but entirely consistent. During the dry period, we see the accentuation of this salt recovery, as we talked about before, and we see high nitrogen, phosphorus, and chlorophyll concentrations in the orange line compared to the blue line. Again, because there is more nitrogen and phosphorus in the system that has come from downstream that is now feeding chlorophyll A to grow. And we said that the blue line is consistent more or less with the yellow dots, which are the field measurements, but the orange line, which is the model predictions from the lumped daily model, is over-predicting chlorophyll because there's too much nitrogen and phosphorus, which is phytoplankton food in the system. So to summarise, Trevor, integrated catchment and receiving water modelling is a really, really important tool we need to use in assessment. And whilst we have always done the best we can with the tools available at the time that we've done our work, sometimes, in my experience, those tools have been disparate in their conceptual arrangement and linkage. With the key issue that for many environmental questions, not all, but many, receiving water modelling is heavily dependent on upstream hydrology models and their inputs. And we saw that today in the Oxley catchment. So we really need to make sure our upstream hydrology is reflecting reality the best we can for the sorts of questions that we are asking. And we've shown that the benefits of high spatial and temporal resolution, at least in the case of Oxley Creek, are really important for getting the receiving water quality modelling right and answering the questions that are being asked of us. That's all, Trevor.
Absolutely stunning. There's so much to be said in such a short space of time, but you really packaged that well, Michael. Philip, thanks so much for that. And Oxley Creek, I respond by saying fantastic example, a wonderful example. I'm going to hand directly over to Emma now for 8 minutes, maybe 8 to 10 minutes of a Q&A. Let's do that, shall we? We can finish around the hour or a bit beyond, maybe. Let's see how they go. Over to you, Emma.
Great. Thanks, Trevor. Look, Michael, that was a great presentation, and we've been answering a lot of questions in the background.
Very good, very good.
Yeah. I guess one of the key ones I've sort of been asked about this is, and maybe this will be actually more directed at Phil, when we're moving away from these lumped models and we're using this rain on grid, how does that impact our run times when we're actually looking at these? And then maybe the second question is back to Michael, is then, do we need to keep these models coupled all the time, or can we look at the individual parts separately? Because I think that's quite an important look when you're calibrating those models as well.
Yeah, in terms of the runtime, yeah, there certainly is some runtime implications for doing that. A lumped model might run in, seconds or something like that. Whereas this was running in about 3 hours to run a year on a decent GPU. In comparison to the total modelling time, I think that Michael said the same period in the 3D model was about 10 hours. Yeah. So we have extended our total simulation time, by a bit significantly, from 10 to 13 hours or something like that. But I would probably argue that the extra benefit that we get in the resolution of those models would probably justify that. But yeah, it definitely is a concern or a consideration.
Yeah, just entirely, Phil. And I think it really does, in my mind, come back again to the questions that we're asking of our models. If we feel that we can run a lumped hydrology model and it can answer the questions that we might be being asked, then there may be no need to run a highly detailed model just for the sake of doing it. But if we are asking questions about detailed hydrodynamics of receiving waters that are really being impacted on a high temporal and spatial scale by complex catchments, like the case is with Oxley, then I think we really need to be paying attention to how we are forcing our receiving models with those upstream hydrology models. And if that means we need to wait a couple of hours for our run to finish in hydrology to provide those hydrologic boundary conditions, then I think that's a really good way to spend a few hours, is waiting for a model to finish to provide information to us that is reflective of what's happening on the ground. I think that's really critical. Because as a receiving modeler, if we don't have that information that's reflective of what's happening in catchment, this makes life so much harder to get that receiving modeling right. So it might seem like a long time to run these things, a few hours, but really if we're running TUFLOW FE for 10 hours overnight, it's not really a long time to wait, but the quality of information we get is so much more of benefit to the receiving water modeling team. To answer the second part of the question, Emma, do we need to run these coupled? We most certainly do not. What we need to do, in fact, the way we've set it up, is that we can have independent teams, if we like, working on the same suite of control files for TUFLOW Catch, working on their respective parts of TUFLOW Catch, whether that's the upstream part or the downstream part, progressively. Now, clearly, we can't do a full calibration of the downstream TUFLOW FE model until we're happy with our predictions from upstream. Obviously, we can't do that. But that doesn't stop us doing things in TUFLOW FE like building the mesh, refining the mesh, testing run times, testing three-dimensionality, getting all the water quality algorithms up and running, making sure the metadata's right, all those sorts of things that take time. We can do all that work at the same time that our catchment models varying our HPC inflows to TUFLOW FE. And we can work on the same file suite. There's a lot of work that's been done in TUFLOW FE without HPC, and there is no need to wait for HPC to be done before we can get started on the FE side of things, and we can have multiple people working on the same suite of files. The only caveat there is that to get that linkage absolutely right, HPC will look at the TUFLOW FE mesh to work out where those physical location points of intersection are. But again, that can happen in its final state when the TUFLOW HPC model is finally calibrated. You can look at the final version of TUFLOW FE mesh and go from there. They don't have to be exact all the way along from day one. They can evolve as time goes through.
That sounds great, Michael and Phil. I think you've answered those questions really well. I think I've got probably time for one more question. And Phil has actually already responded to part of this, I think. Within TUFLOW Catch, are we able to represent any storages within the catchment? And then how do we represent the different, I guess, soil characteristics, say from someone in WA, Western Australia, compared to what our soil characteristics around here, and how does the TUFLOW Catch model deal with that?
Yeah, in terms of the TUFLOW HPC side of that, those storages, typically like dams and things like that, we'd probably want to represent those in the 2D, so that the 2D cell is representing the elevations. With the subgrid sampling, it's building up a curve essentially of elevation over height, so that even if our TUFLOW cell is we don't have multiple cells across a storage, the subgrid sampling should be allowing us to actually represent the storage characteristics of those. And in terms of the soils, we were using a green amp soil infiltration. So for the very top layer, so where we've got water infiltrating from the surface layer into the soil, we're using a green amp type approach, a green amp equation, and then that goes into the groundwater layers, and then we can have up to 9 vertical groundwater layers, vertical soil layers, which have a hydraulic conductivity between those. So we've got a vertical and a horizontal hydraulic conductivity, which controls how it goes through the profile and also how it goes sideways. So, in WA, you're probably running as a sand or a sandy loam or something like that, because it all just disappears, whereas, you can have clays and loams. So they can either be as predefined soil types, or you can specify those green amped parameters in terms of how much is allowed to go in. And that can vary across the model. You can have you have numerous soil types. It's not as many as you want, but I think the limit might be 256 or 1,024 different soil types. You're probably not going to get to that level of resolution. And they can also vary on a cell-by-cell basis in terms of how deep they are as well, in terms of the profile. It's entirely up to the user input and if that data is available.
I might just add to what Phil said there, Emma, from the water quality receiving modelling point of view. The way that TUFLOW Catch works is that it interrogates some basic, uncalibrated, but basic structural information about TUFLOW water quality module, and therefore expects same information in terms of pollutant accretion and release to be specified by the user. So the TUFLOW FE model set up with just inorganic nutrients, then inorganic nutrients will be able to be specified in the catchment side of things, and there will be no limit. As complicated water quality as I can think of, there'll be no limit in terms of the catchment number of traces that can be used to simulate those processes. So really, we're getting away from saying you can only simulate 3. It's dynamically determined with large limits, so that effectively they're unlimited for practical purposes. And all those traces get transported in the surface and the subsurface.
Great. Thanks for that. Trevor, I don't know if we've got time for any more, if we've hit our limit.
Let's just do one more, shall we? We reckon another 5 minutes will be fine, but let's do another one. It's going so well. I mean, we could go for a long time. We can see the questions aren't reducing, they're only increasing.
I actually think there's more and more coming now. There were a couple of questions about sediment transport and how you would actually model that, whether that's within that catchment or receiving model, and can you actually couple the sediment modules to that to look at bed erosion?
Yeah, indeed. There is no hard and fast rules about where we should build our TUFLOW FE model to in terms of going back up the catchment. There are many models that we've built over the years where we have TUFLOW FE models going from effectively 0 AHD tidal areas up to 200 or 300 metres above sea level. That's a TUFLOW FE model. If we did that, we therefore have TUFLOW FE resolving all the run-of-the-river processes and in-stream processes, one of which is sediment erosion and resuspension. So again, if we had a question that was asking us about a particular river reach that sediment erosion or deposition was an issue, we would build our TUFLOW FE model to encompass that reach, and then allow TUFLOW Catch to dynamically link, like we've been talking about, into TUFLOW FV up in that part of the catchment. We wouldn't build our TUFLOW FV model out of the bank too much. We would let it do in-bank erosion and deposition as being forced by sediment predictions from TUFLOW HPC. But we shouldn't think that TUFLOW FV is limited to tidal applications.
Great, thank you. I think that's all the questions that I've got there for the moment. I know there's a few others being answered by Chris in the background.
Well, that's great. Should we halt it there? I think you're in the practice, TUFLOW, of picking up these questions and doing them out of session. So do you think that's a good way to get travel? Are you happy with that, Michael?
Absolutely. Oh,
yeah. Yeah, absolutely, of course. Yep.
Okay,
we'll answer all these questions and post them with the video at the end on the AWS website so people can access the complete Q&A, even ones we haven't answered yet. We'll answer them in the coming days.
Thanks very much, Chris. Hear that, and Emma. It has been an awesome session. There's just so much to be done here. You're doing too much in a short space of time, of course. Recording will be emailed to you, uploaded to website and YouTube channel. As a live attendee, you'll get a certificate. And please stay on the line just for 1 minute to give us your thoughts. I think it's just tick answers, but I don't think it is. Just tick box answers, and that will help us shape our future webinars. It's been a really great day, Michael, Emma, Philip, Chris, and the team at AWS, Joel particularly, and Renee. Thanks for making this just come alive. You can see what's happening here. It's getting bigger than better. Webinars, 3 of them, they're coming up. Live courses. Webinars are free, of course, and live courses and the AWS on-demand courses. After 10 years, this has been a big party. You know, one thing I did think as you were speaking, Michael and Phil, Emma and Chris, was that the environmental practitioners must be dancing at the moment to have a functionality like this was only dreamed of 10 years ago, if I'm right about that. Is that a fact?
I think that's probably the point, Trevor. Yeah. Things have moved really fast. We're supposed to be fast.
Yep. No, wonderful. Thanks again, team, TUFLOW and everyone involved today. We'll call it a day there, but keep tuned in, everyone. Thank you for your questions. They've been in-depth, and we've really appreciated the discussion. See you again next webinar. Bye for now.
Thanks, Trevor.
Thank you.
Yeah.